Hello everybody, it's Marco here. This is my first time as a speaker and I'm glad to be here at Conf42 to bring some goodness in Go. So let me introduce myself. So I am a software engineer at Ion. I'm a master degree student in AI at University of Pisa, and I'm into everything that is related to cloud native and Kubernetes. I also participated at the Closer 2023 Cloud Conference, and fortunately I won the Best Paper Award. And the work I proposed in that conference was something related to how to solve smells in a Kubernetes microservices environment. So let's go ahead, and I'm going to introduce you some topics that you might already know, the more expert might already know, but still I think it's still interesting to catch. So as a first topic, I just want to go deep down through the Go runtime scheduler and the memory model and how they are impacting the performance of Go applications, and then how to measure your applications and find bottlenecks if there are any, and then some best practices. But first things first. So Go is a fast language, but why? What makes Go stand out in the gorgeous realm of programming languages when it comes to performance? And to ask to that question, we need to look under the hood and examine two fundamental aspects of Go, that is the memory model and the runtime scheduler. So, but let's switch from Go a little bit to Java. Okay, so some of you already know that Java uses native threading as of operating systems, right? So that means that every Java thread is mapped to one kernel thread. In this way, Java cannot determine which thread would occupy the core, and this is completely up to the OS scheduler. So it's completely dependent on how many threads you have, right? So a problem could be, for example, if I am executing a Java thread inside a certain OS kernel thread, I save the state, and then the Java thread is scheduled into another OS thread. Then I would suffer from context switching, and we will see an example. Let's do a Java example here. I have a function that does something, as we see, for x times, and we have a number of threads that are executing this function this number of times. Now, if I run that code with 100 threads, okay, and with 1,000 threads, we have different results, right? So you can see that in the picture. Basically, when the number of threads is set to 100, about 51% of the CPU time is spent in the function do something, so our real function. But then when you increase the number of the threads to 1,000, the CPU time spent for the actual function went down about 27%. And all of these metrics basically are telling us that the cost of the thread, the Java trading model, suffer in a concurrency scenario. So in standard operating systems, the threads are scheduled after a certain amount of time, and when a hardware timer interrupts the processor, the OS kernel suspends the current executing thread, saves its state in registries, so when it has to resume it doesn't lose anything. And then it finds among all the threads available for being executed the next one-to-one. And as I said, this is called the context switching process. And this process is kind of slow, even because, as I said a couple of slides before, there could be like a cache miss, okay? So this is the main reason why the co-founders created the Go runtime scheduler, okay? So Go doesn't totally rely on the OS scheduler, but it has its own runtime scheduler, and it uses a threading model called MN threading model, where basically M Go routines are being scheduled among N OS threads. So as we can see here, there are kind of, let's say, interfaces between the Go routines and the actual kernel threads. So the kernel threads in this picture are the white triangles, and the Go routines are the one. The Go routine can be green in this case. That means that is actually running if its thread is in the queue. But that yellow boxes act as an interface, and those yellow boxes are the context, okay, that are fundamental. So once a context has run a Go routine until a scheduling point, it pops a Go routine off the queue, sets the stack and the instruction pointer, and begins running the Go routine. And what can happen is that a yellow box, in this case a context, is running out of Go routines, and automatically, without basically calling any kind of interrupts, it automatically still Go routines from other contexts. And this makes sure that there is always work to do on each of the contexts, which in turn makes sure that all the threads are working at their maximum capacity. So taking advantage of this runtime scheduler, Go was built upon a CSP model. CSP stands for Communicated Sequential Processes, where basically we have Go routines, and these Go routines can communicate each other via a channel that can be buffered and buffered. But the cool thing is that we as a developer, we don't have to care about basically accessing shared data. So we don't have to set matrices or semaphores or locks or queues and other things like that, sync variables and other things like that. So this is really, really cool in Go. This is something that I really appreciate because I love writing pipelines, for example. So for the pipelines, this kind of model is really cool, even because the way the two Go routines, as they are not threads, are communicating is really fast. Let's go back with Java and just do a comparison. So we have this code here. We are doing a sleep of 10 minutes, and we are using 1,000 OS native Java threads, right? And at the end of the execution, we can see that there are actually 1,000 threads plus 18, and that 18 is the number of threads occupied for handling the JVM. And the real power that we encounter when we're executing code is especially on the number of threads used, because the same code actually needs only 2 threads, and this is really cool. We said that a couple of steps before that the Go routines save their state, right? So Go save the Go routine state. But let's do a comparison on how OS threads are saving the state and how the Go routines save their state. So the OS threads have a fixed size stack for saving the state, but this is kind of a problem because it is kind of a huge state waste of space if we imagine that there is a single Go routine, but at the same time it can be too strict for hundreds of thousands of Go routines that are being created, which is not a rare event in a Go-based application. Therefore, the Go memory model works in another way, even because we won't have a good amount of Go routines. In contrast to the approach that we saw before, Go creates very small stacks for each Go routine, around 2 kilobytes, and the surprising thing is that each of these stacks is growing and shrinking as needed, and this is possible because of the capability of these stacks to borrow memory from the heap. And the fact that these stacks are dynamic allows us to have better memory management. And as the memory overhead is reduced when context switching happens. And that's because of the small states we have to save for each coroutine. So this was like a sort of introductory topic for the new for the new Gophers. But once we let's assume that you now know very well this concept and you started take all the goodness of Go for your applications. So now, how we can measure the performance of your Go applications in a systematic way? Before starting explaining how to benchmark the applications, I want to do some preconditions. So the precondition is that every time that we run our benchmarks, when you run benchmark, you want to always keep the same environment. We don't want to get affected by the external environment. So, and another thing that is crucial to do is to isolate the code that is being benchmarked from the rest of the program. So how to write a benchmark? So this is a practical slide. So we create an underscore test.go file where we put all the benchmark functions, and the benchmark function as a specific signature, and we have to specify the B variable that has type testing.b. And as we're gonna see right now, for example, in these two, as we can see later on, that this b.n represent the number of iterations that dynamically the Go runtime decide for your function to run. Okay, so you don't have to touch that variable at all. Okay, so it's totally up to the Go runtime to decide that how many times to iterate your benchmark. So let's take two functions here. We have two pipelines. So the pipelines are, these two pipelines have the same structure. There are a producer that is producing some strings. Then there is like some stages where basically we take all the strings, we lower them, then we merge the results from the old coroutines, and then we send them concurrently into the other stage, which basically takes the string and capitalize the first character, and then merge all the result, right? So they have the same structure here, but they are different under the hood, right? So we want to benchmark these functions, and we now can do a smart thing. Since we want to use a tool called benchstat. So benchstat, what it does is to compare two benchmark results, okay? But in order to compare these benchmarks, the benchmark function must be the same, okay? So a cool strategy could be to first create your benchmark, then call the function, for example, run pipeline 1. You produce the benchmark as we do in the first, in the second image. So we return the output as a before.bench, and then we can go back to that same benchmark function and change the inner function. So instead of run pipeline 1, we run pipeline 2. Okay, so the result is in the first, is in the number 1 code. Okay, so now we have two benchmarks. But before doing the benchstat and comparing them, we can open one of them. For example, we can open the before.bench. Okay, so how to read a benchmark. So we have 4 values, and let me switch back, because an important thing is that we have to see those flags here. So the -run equals to X means that basically what the benchmarking engine does is, okay, I see the run pipeline function in the benchmark function, so I need to run all the tests related to that function. And I'm lazy, I didn't want to do that, so with the -run equals to X, you avoid that. And also another important flag is the -benchmam that allows you to keep track of the memory used for your functions. Now we can go ahead. So with that command, we get this result. Okay, so we can see in the red circle that there is the number of iterations, so the b.n that we mentioned before, and this is the blue circle is one of the most important, because it explains to you on average how fast your application is in terms of nanosecond per operation, the number of bytes per operation, and the number of allocs per operation. And the last 2 results came from the fact that we used the -benchmam flag. So let's go ahead and let's use benchstat, which is a really great tool to compare to benchmarks. And as we can see, okay, so the before.bench was running the run pipeline 1, and the after.bench was running run pipeline 2. And we can see three rows. Okay, the first row is the speed. The second row is how much memory used your function. And the third row is how many allocations your function did during the benchmark. And we can see that the run pipeline 2 is faster by 40%, is wastes less memory a lot, like 40%, and it allocates less than the run pipeline 1 does. Okay, so almost 86%. So this is kind of a systematic way to measure your applications. But now, you maybe are wondering why the run pipeline 1 function is slow, since the structure is the same. So here comes profiling. Profiling is the process of keeping track of all the inner functions that your main function runs, and it allows you to track the CPU and the memory of all the instructions. Okay. For doing that, we use a pprof. Pprof is a tool for visualize the profiling data, and it's available for free, of course, as a Go tool, and it's based on protocol buffers. So, in order to exploit this pprof, now we want to add 2 more flags, which is the CPU profile and the memory profile. And we load the result of the profilings, one for the CPU and one for the memory, into 2 different .prof files that are basically protobuf type files. Okay. What if we run the pprof? As we can see above the line above, there is go to pprof CPU 1.prof. Now if we go back in the slide before, there is no 1 at the end of the -bench flag. That means that all the benchmark functions that has that prefix starts. Okay, and in that case, I put basically the benchmark pipeline 1 and separated the benchmark pipeline 2, so that we can compare using the profiling the 2 functions. Okay, so using this command, okay, I'm inside the pprof and I can run the top 100 command. So the top 100 command gives me the most 100 CPU expensive tasks, and I can see that, for example, there is a sleep, and we have the strings.lower function. Another important thing is that in the top list, there are basically only stages that comes from the run pipeline one function. And we're not seeing any kind of function from run pipeline 2. And that's because, of course, we saw before with the benchmark that run pipeline 1 runs actually slower. Okay, since this list is in descending order of how much time has been spent. So we are suspicious. We are a little bit suspicious here. So and instead, if we scroll down, we can see our fast stages. So we're a bit suspicious here. So what we can do is to dive into the code of run pipeline 1. So we run again the pprof, and we can use the list function, the list method of pprof, where you can basically say which function you want to analyze. In this case, I want to analyze the first stage of the run pipeline 1, which is transform to lower 1. And if I go inside, apart from the code above, okay, we have to focus on the red box, and it seems that we are losing time here, okay, because we see that we are doing a loop, okay, where we are lowering character by character, and then we return the result, okay. But this is kind of a problem because we know already that there is a function that this is coming from the strings module that is lowering our strings in a faster way. Okay. So let's analyze the faster one. Okay. So as we can see, we have the strings.lower function that is coming from the module, and it takes 26 seconds. Okay. So overall, we saved almost 5 seconds, because here we have to take into account this amount of time, so 70 seconds, but we also have to take into account the time that has been spent to send the data to the channel, that is almost 13 seconds. Okay, so here's why there's the difference. So it's 13 plus 17, okay, rather than 26 overall, okay. We found out why our function is lower, okay, but we now analyze the CPU profile, okay, but we also produced a memory profile, and as you can see, for example, is that in the slower function we have a waste of memory and waste of we have an enormous quantity of allocations. So of course, this is what I wanted to show you, right? So the systematic way to find out where your program is low, where your program is fast, okay? So, but before concluding, a suggestion is that I want to like that to be completely accurate, any benchmark should be careful to avoid any kind of optimisations that the compiler does. For example, if we don't save the result of the run pipeline, sometimes it happens that the compiler eliminates the function under the test, and somehow it artificially lower the runtime of the benchmark, and we don't want that. When utilizing the profiler in Go, it's important to consider that it samples both CPU usage and memory at specified frequency, okay? However, this sampling may not always be 100% representative, particularly if the sample time is very low. So to enhance accuracy, I recommend increasing the bench time parameter accordingly, okay? So in this way, you allow the profiler to collect more samples over an extended period, and then we can obtain more precise insights into our application's performance. So, of course, try to design your applications as a pipeline of Go routines. Always keep track of the memory usage, as it can cause garbage collection to run, and therefore that means that we potentially wasting time. And of course, as I said, as in the precondition, try to execute benchmarks on a stable machine without having spikes during the test. So here I left some study references that I really found that interesting. So how Go-routines works, how the memory model works, and the scheduling works, and how you can use benchmark and profiling to improve your function's performance. So that's it. Thank you for your attention. Hopefully this was an important way, an important moment for you to learn something more about Go. So I'm really excited to hear you in the comments, and so that I can improve my my speaking skills, as this is my first time speaking in public. So really speaking with the bottom of my heart. Really thanks, and I hope that this is the first of an infinite number of speakings. Okay, so thank you guys, and have a great day.